Greetings! Welcome to Electronic Circuits 1. My name is Behzad Razavi and I will be your guide on an interesting journey through the world of electronics. As you know, electronics has affected our lives in many different respects, and today we can see it everywhere. And our objective in this course is to build the foundation for analysis and design of electronic circuits. Today, what I would like to accomplish is first give you an introduction to electronics and then start with semiconductor physics. The devices that we use in electronic design are based on semiconductors, and to understand how the devices operate we need to understand semiconductor physics. So for that we'll go over some general concepts that are familiar to you from physics and chemistry, and then we will look at the concept of doping as one method that we use in semiconductor devices. All right, so before we go there, let's just take a look at what we learned in basic circuit theory and what we are hoping to learn in this course. So, all right, well, in basic circuit theory, we learned, of course, circuit theorems, KVL and KCL and Norton equivalent and Thevenin equivalent, etc. But we also had a few devices, a few components that we could play with. Resistors, capacitors, inductors, maybe transformers. But they were very few in number. So we had only resistors, capacitors, and inductors. So this is what we call, what we would say, basic electric components. And with such a small number of components, especially only two-terminal devices, it's very difficult to build many useful and exciting circuits. So if you recall from your circuit theory courses, they didn't really have that many applications from real-life examples of the circuit design. On the other hand, in electronics, the world is different. So in electronics, in addition to these basic components, we have some other components that suddenly open up the horizons for circuit design. We have, for example, diodes. Of course, we don't know what they are right now. And then we have transistors. We have two types of transistors. We have bipolar transistors and MOS transistors. And then we also have what we call op-amps. You might have seen them as a black box before. So an op-amp looks like this. It's an amplifier with two inputs. So with so many devices available, suddenly we can build much more complex and sophisticated circuits. And that's why electronics is so exciting. Every day we come up with new ideas, new ways of connecting these things together. You can imagine how many combinations and permutations of these devices can exist. And that's why it's interesting to study electronics. All right. Now, but because these devices are based on semiconductors, we do need to understand semiconductor physics to some extent. Just the way an engineer designing an automobile needs to know how the engine operates, how the carburetor operates, everything else, we also need to know how this device or that device operates internally. So for that, we have to start with semiconductor physics. The semiconductor physics that we cover here is not as deep as what you would see in dedicated semiconductors courses, but it's just barely enough for this course. It's a little boring for the next one or two lectures, but you have to bear with me so that you understand this stuff, and then you can move on to more exciting circuit examples, etc. All right, so now based on these, we can figure out what topics we will cover in this course. So the outline of this course is like this. We start with semiconductor physics, which is the foundation for all of these devices. So semiconductors or semiconductor physics at a simple level. And once we understand that, we can go ahead and build each of these devices. So we go ahead and build a diode and understand its inner workings, and more importantly, find out how we can model this. We remember that a resistor satisfies Ohm's law. We remember that a capacitor satisfies I is equal to C dV over dt. How about a diode? What model, what mathematical expression should be used for the diode? And once we know that, we can go and build circuits out of diodes. So we learn about diodes, and then we go to diode circuits. Are these useful? Absolutely. You have them everywhere. You have them in your charger that charges your cell phone. You have them in your laptop, everywhere. So it's good to know how diode circuits operate. All right, then we'll repeat this for these other devices. So we go to, for example, bipolar transistors. And once we know how they operate and how we can model them, we can go ahead and build circuits out of these transistors. So we build bipolar circuits. And finally, for MOS devices, so we go to MOS transistors, and after understanding their operation and their modeling, we can build MOS circuits. At the end of this course, we will also look at circuits that incorporate op-amps in them and perform interesting functions. So at the end of the course, we'll also look at what I call op-amp-based circuits. And this will take us about 45 hours of lectures. Okay. All right, so with this, we now have a clear picture as to where we will start and where we will end. And we're going to start with semiconductor physics, trying to understand what a semiconductor is, what it means, and then how we can modify it, how we can play with it, etc., until we can build a diode from that. That is the objective as we go along. In this course, we will also have what I call the Frontiers in Electronics series. The purpose of Frontiers in Electronics is to give you examples of applications of electronics in daily life. This helps us appreciate the beauty of electronic circuits and also see how what we learn in this course becomes useful in everything that we see out there today. So we have many examples of electronic devices in our lives. For example, cell phones and GPS and Wi-Fi, etc. Today we will spend a little bit of time on the cell phone itself and see how it might operate. Our treatment is very simple. At the level of our understanding in electronic circuits 1, we're not pretending that we can design a cell phone or we can even repair a cell phone. We're just trying to understand how it generally might operate. Anatomy of a cell phone. So we would like to see what exactly is going on inside a cell phone when our voice or data is communicated from one place to another place wirelessly. Now, our treatment is at a simple level. So we will just look at the general functionality that we would have in such a system. Well, a cell phone would consist of a transmitter to transmit the data or voice or video of interest, and the receiver to receive that, process it, and retrieve the information. Okay, so what do we need to build a wireless transmitter? Well, first we need an antenna. So let's pick an antenna here. That's the symbol for an antenna, which takes an electrical signal and converts it to an electromagnetic signal so that the waves can propagate through the air and get to the receiver. All right, now we have, let's say, my voice, which goes to a microphone. So here's a microphone, mic, And the microphone generates an electrical signal. So if I plot that as a function of time, it looks like this. So that's what we get at the microphone. So the question is, can I just connect the microphone output directly to the antenna and let it convert it to electromagnetic waves and send them out? So can I just short this from here to here? Now, of course, you may say, well, the microphone signal is very weak, so you should probably amplify it before you do anything with it. So that's true. So let's put an amplifier here. This is just a very simple audio amplifier to amplify the signal that's generated by this microphone. Typically, the swings that you would see at the output here are on the order of a few millivolts, maybe 10 millivolts, so we would need to amplify them. But can I go ahead and connect this point to this point? Well, no. And the reason for that is that for an antenna to be a good antenna, meaning a good radiator of electromagnetic energy, its dimensions, however they are, whether it's round or rectangular, etc., its dimensions must be comparable to the wavelength of the signal that we apply to it. So, for example, if you consider this transmitter that is connected to my microphone, this transmitter has a small antenna inside. We don't see it. This transmitter operates at, I don't know, 500 megahertz, 600 megahertz. The antenna is about this size and somewhere inside, or maybe a loop or something. All right. So we need a frequency here corresponding to a wavelength that is reasonable in terms of these antenna dimensions. On the other hand, the signal that is produced by the microphone, the audio signal, the voice signal, has a frequency range of 20 hertz to 20 kilohertz. And if you do a quick calculation, you will see that the wavelength associated with these frequencies is extremely large. So there's just no way that we could connect an audio signal directly to an antenna and hope that antenna with any reasonable dimensions would be able to radiate. It would not radiate. So what do we do here? Well, what we should think of is start out with a frequency that is friendly to the antenna. So maybe 1 gigahertz, 2 gigahertz, whatever we want. In cell phones, we have 900 megahertz, we have 1.8 gigahertz, 2 gigahertz, 2.2 gigahertz, so something like that. So we start out with a frequency that is good for the antenna. So here's a frequency. I will just say 1 gigahertz as an example. 1 gigahertz. And what we are hoping is that this information can be somehow combined with this frequency, so that this frequency, this waveform, carries this information for us. And then the result is applied to the antenna. Is the frequency high enough that the antenna dimensions would be reasonable and everything is good. So we call this waveform the carrier because it will carry the information that we would like to transmit. So this is called a carrier. All right, now how do we combine this information with this? In other words, how do we impress this information upon this carrier? Well, you can imagine we can change the amplitude according to this information, or the frequency, etc. So there will be some sort of change or modulation, as we call it, in the properties of this carrier according to the signal that is produced by the microphone. So that calls for some box, which we call the modulator. So here's the modulator, and the job of the modulator is to take the information signal that we are producing from the microphone or from a camera, etc., and take this carrier, combine these somehow, and give us a result that has this information on top of the signal. Okay? All right. Now, this is ready to be transmitted. The frequency of the signal is high enough, let's say 1 gigahertz, that the antenna would be of reasonable dimensions. But if we are hoping to transmit this information over a long range, let's say a mile or 2 miles or 2 kilometers, etc., then we might want to apply a large amount of power to this antenna. And for that, we need another amplifier placed between the modulator and the antenna, and this is called a power amplifier. So here we have a power amplifier, a PA. A cell phone might transmit 500 milliwatts, even a watt at this point, so that goes a long range. All right, so we see most of the blocks that we would need. Some sort of processing of the audio signal, a modulator, a power amplifier. Now this carrier has to come from somewhere. Where does it come from? It's a periodic signal, so we may think of an oscillator as a circuit that produces a periodic signal. It oscillates, so it keeps producing a sine or a cosine or a square wave or something. So this will come from an oscillator. So you may have a 1 gigahertz oscillator or a 2 gigahertz oscillator, and the signal comes here. This is called the carrier signal, or sometimes we call it the local oscillator. And then we somehow impress this information on this, maybe modulate its amplitude or its phase or its frequency, and then we go through the power amp and we come out. All right? That's the most basic transmitter that we can build. Okay, now let's go to the receive side and see what should happen there. We sort of expect the reverse of all of this to happen, right? So let's see what we need to do there. Okay, I will draw the receiver on this side. These waves propagate through the air and are picked up by my receiver antenna. So I have an antenna here, and I'm trying to build my receiver. So here's the receiver. So I guess I should call this the transmitter. And by the time the waves get to my receiver, they are actually quite attenuated. So this wave will be very little by the time it gets here, if it's a long distance. And the signal that comes in is so small that we can't do much with it. So that calls for amplification. So we need an amplifier right here, which we call a low noise amplifier, and LNA. And now the signal is a little bigger, so we can play with it. And then we have to go through some processing, maybe demodulation or whatever it takes, so that at the end we retrieve this original signal. So I'm hoping that now in my receiver I take back that audio signal, I can apply it to speaker, and I can listen to it. So there will be some processing here. I know this is vague, but in the interest of time, I won't go through the details of this processing. And then here, eventually, we give the signal to a speaker, and that produces the audio signal back for us. This is the journey that the voice signal takes, as it starts from this microphone, goes through the air, is received by the receiver, and processed to generate the voice signal. You can imagine that there are many other building blocks in here that we are not talking about. In a cell phone today, we have a great deal more complexity than what we see here. But this is the bare bone structure at our level of understanding that helps us appreciate what we have here. So we see some functions that are very good and necessary. We have amplification. Amplifiers here, 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 maybe more down here. We have oscillation. To build an oscillator, we actually need amplification. So we have some sort of amplification that is converted to an oscillator. So we need here. There are also some interesting functions inside here and inside here that we are not covering at this point. Very well. Let's begin with semiconductor physics, and we start with some general concepts. So let's begin with our general concepts. Okay, well, we know that atoms consist of a nucleus and some electrons surrounding the atom. And of interest to us, this is the nucleus, and there are electrons in these various shells, or as we call them, orbitals. And of interest to us are the electrons in the last outer shell of the atom. So we have some electrons in the last shell, or in the last orbital. And these electrons play an interesting role in how these atoms interact with other atoms. All right, so these electrons out here, electron, these are called valence electrons, the ones in the last orbital, the outermost shell. Different atoms have different number of electrons in their valence, among their valence electrons. So, as an example, we have sodium. Sodium has only one electron in the outermost shell, and as a result, it's very reactive. It wants to get rid of that electron as soon as possible. So sodium reacts with everything else very quickly. Then we have, for example, neon, which has 8 electrons. And that means that its orbital, its last orbital, is complete. So it has no tendency to interact with anything else. We call it noble gas, so it has no interaction. All right? And then we have, for example, silicon. And silicon happens to have 4 electrons in its outermost shell. 4 electrons. So silicon is not as reactive as sodium or as inert, as non-reactive as neon. It's somewhere in between. So it could interact with other atoms to some extent. And this is the foundation for semiconductors that we study in this course. All right, so that's the silicon atom. And let's try to do this. Let's try to build what we call a crystal of silicon. A crystal of silicon is a very regular array of silicon atoms placed very neatly next to each other. So here's how it goes. We have the silicon atom here, another silicon atom here, another one here, and so on. So we have another one here, etc. This silicon atom has 4 electrons available in its outermost shell. So what it does, it begins to share these electrons with the neighboring atoms. So now this silicon, some of the time, has 8 electrons, so it's complete, because it has 4 of its own, and then it's borrowing 4 from these 4 neighboring atoms. And so on. This continues everywhere. These bonds are formed everywhere. So you can see that this is a very regular and clean array of atoms, very organized, and that's what we call a crystal, or we call a lattice. So silicon has the ability to do this. With proper processing of silicon, we can create silicon crystal. And that's what we use in semiconductor physics. All right, so let's say that I have a piece of silicon that I bought, and it has this structure in it. And I'm wondering if this can conduct electricity. So I come along and I apply, connect a contact here, a piece of wire on each side, and I connect a battery here with some voltage, V1, let's say 1 volt or 2 volts or something, And I'm curious to see if there's any current flowing through the semiconductor. All right, well, for the current to flow, we need some sort of maybe electron to flow, some sort of charge carrier to flow. So we need perhaps an electron to start from here and travel all the way this way, right? Going from the positive end to the negative end. So we need an electron. Do we have an electron available here that can take off and go around and carry charge? It seems that the electrons are all occupied. They're all bound to these atoms. It seems that no electron is free. This electron is shared between these two, this electron is shared between these two, etc. In fact, if we perform this test at absolute zero, that is exactly true. At absolute zero, these electrons are all connected to these atoms and have no way to go. But at any finite temperature, because of the ambient energy that we have, the thermal energy that we have, once in a while, one of these electrons comes off from that bond and is available to move around. So statistically speaking, at any temperature, some electrons are free because they just come off of these bonds. So this might, instead of this, we may have a free electron that becomes available. And now, yes, if we apply voltage, some of these free electrons can conduct electricity around this loop. All right, so a piece of silicon can conduct electricity at a finite temperature, let's say at the room temperature. And for that reason, we call it a semiconductor. It's not as good as metals, which are very good conductors, right? And it's not as bad as, for example, diamond, which is an insulator. It doesn't conduct. It's somewhere in between. It conducts to some extent, and that's why we call it a semiconductor. Very well. So that's what we have for the crystal and the silicon, the piece of silicon. Okay, so in this study, we need to answer a number of questions as we go along and understand these principles. So let me write these questions here, and we'll try to answer these questions one by one as we go through the physics of semiconductors. So let's add a page here. Okay, so we are dealing with currents and voltages in semiconductors. Currents are carried when an electron, for example, moves around, or generally a charge carrier moves around. So the first question is, where do charge carriers come from? So let's write that down here. Where do charge carriers come from? Well, I just mentioned that in a piece of silicon, we do have electrons, charge carriers, at a finite temperature because of the thermal energy. Once in a while, the electron inside the atom, inside the valence band, has enough energy to come off and become a free electron. But is that the only type of charge carrier? Maybe there are other types of charge carriers that will come along as well. So for the second question that we want to answer in our studies is what types of charge carriers do we have? The most familiar to us are electrons, but are the electrons the only types that can conduct a current through a piece of semiconductor or any other piece of material? So we would like to answer that question as well. Okay, so then once we understand these two, we need to go and ask the following question. How can we modify the density of charge carriers? Intuitively, we know that if in a material we have lots of carriers, then that material is very conductive. If you have very few carriers, it's not very conductive. So that's what we call the density of carriers. Now, if I give you a piece of silicon and it has some number of electrons per cubic centimeter or cubic meter, and you're not happy with that number, you want to increase it or decrease it, how do we exactly do that? How do we make sure that this piece of silicon has a higher number of free electrons available for current conduction or a lower number of electrons available? So that's what we call modification of carrier densities. So we'd like to see how that works. And the last question that we need to answer in relation to semiconductors is, how do charge carriers move? That seems a logical question, right? Because we are interested in how current is created in a semiconductor. So if I say these electrons are going from here to here, by what mechanism are they exactly moving? And we need to understand and be able to quantify that mechanism. So we will look at that at some point. All right. So we have partially answered this question. We saw that the electrons are freed from the bonds inside the silicon crystal. But there are other interesting questions that we need to answer. So let's go and try them one by one. All right. So I need to introduce another concept that is necessary for us to understand these questions. So let's talk about that concept for a few minutes, and then we go back to these questions. In the meantime, I go to a new color. So this is what we call, what happened here? Okay, we call it concept of band gap energy. Now, along the lines of what we just discussed about a piece of silicon and some free electrons that we can find there, here's what we would expect. Let's try to plot as a function of absolute temperature the density of free electrons in silicon, just very qualitatively. So this is density of free electrons in silicon. This means that if I go take a piece of silicon at some temperature, room temperature for example, and I go and look at 1 cubic centimeter, and I count how many free electrons we have, that would be a value here. All right, so as I said, at absolute zero, we have nothing. So at absolute zero, everything is frozen. We have no carriers available. And generally what we know is that as the temperature goes up, more electrons have a chance to break free because of the higher available thermal energy in the ambient. So, in the ambience. So, we have to have some behavior like this. Now, whether it's linear, nonlinear, we don't know at this point, but it has some sort of behavior. We know that it has to increase with temperature. Okay, so that's fine. But something interesting happens if we study two different types of elements. For example, let's say this is for silicon. Silicon has 4 electrons in its outermost shell, and it has this type of behavior. Now, if I go to the periodic table, I can find another element that also has 4 electrons in its outermost shell, and that's germanium. So for germanium, if I try to construct the same plot, I will see something like this. So that's germanium. Both of these are in the same column in the periodic table, and they both can be used as semiconductors. All right, so why is it like this? Why is germanium density of free electrons a stronger function of temperature than silicon's density. Okay, so we are hoping that maybe there's one equation that can describe both of these, and there's only one number in there that depends on silicon or germanium, right? And in fact, that equation exists. So we'll try to write an equation for this behavior. So here's what we'll write. We'll write the density of electrons. We'll denote that by n. N is the number of electrons per cubic centimeter. And then we'll write I. This is called for an intrinsic piece of silicon. We don't know why it's called intrinsic at this point, but don't worry about it. We'll see that later. So intrinsic silicon, and N is the density of electrons, the number of electrons per cubic centimeter. So there's a nice equation for this that gives us this behavior. So let me write the equation. It's 5.2 times 10 to the 15 times t to the power of 3/2 times exponential of minus Eg over 2kT. All right, so let me walk you through these. We have some number times the absolute temperature to the power of 3/2 multiplied by this exponential. This exponential has something here which we call the band gap energy. So this is called the band gap energy. And what it really means is the amount of energy that an electron needs, let's say in silicon, to break free from the bond inside the atom and become available for current conduction. So that's the amount of energy we need. And this immediately tells us something. It says that in silicon, we need a higher energy, we need a higher temperature to get the same amount of, the same number of electrons per cubic centimeter as germanium. So that means that Eg is higher for silicon than for germanium. Now K is Boltzmann's constant. Boltzmann's constant. And its value is good to memorize. You will encounter this many times in electronics. It's equal to 1.38 times 10 to the minus 23 joules over Kelvin. And T is absolute temperature. Okay, so what we see is that this equation applies to both germanium and silicon. The only difference is that Eg has different values for different elements. So let me write that here. Eg is approximately equal to 1.12. The unit is a little strange. You might remember this. The unit of this energy is electron volts. Similar to joules, but this is more convenient. Electron volts. Electron volts means the amount of energy that we need to take one electron across 1 volt of voltage difference. And this is for silicon. And then for germanium, it's lower. For germanium, it is 0.67 electron volts for germanium. So that tells us why we have a stronger function here for germanium than for silicon. All right, and then finally, if you're curious, for example, for diamond, is 2.5 electron volts for diamond. And that's why diamond is such a good insulator. As for diamond, this would be way down here because of this exponential relationship. So diamond has very, very low current through it, so it's considered a good insulator. All right. Now, with this in hand, we can go ahead and look at an example. So let me use these equations to just give you an example. So here's an example. For silicon, let's go ahead and calculate Ni. So at T equals 300 Kelvin, we have Ni equals, so we go place 300 here. Eg is 1.12 electron volts. You have to worry about these units, etc. K is this much, T is 300, do the calculations, and Ni comes out to be approximately 10 to the 10 electrons per cubic centimeter. These are the number of free electrons that we have at the room temperature. So if we take a 1 centimeter by 1 centimeter by 1 centimeter a piece of silicon crystal, as I showed you before, right? So this is 1 cubic centimeter. Then inside here we have 10 to the 10 free electrons. Okay? So that gives us a feel for what kind of electron density or conductivity we might have in a piece of silicon at the room temperature. All right, now this number, 10 to the 10 electrons per cubic centimeter, doesn't have too much significance for us. We don't know if this is a large number or small number or what. So somehow we have to compare this with something else. We don't know if this is this considered a really good conductor because we have 10 to the 10 electrons in 1 cubic centimeter or not. Well, we have to remember how many atoms of silicon we have in 1 cubic centimeter. And that number is the following. So 5 times 10 to the 22 silicon atoms per cubic centimeter. So in this little piece here, we have this many atoms, and of those, only this many electrons have been freed. So if you look at the ratio of these two, we see that a very, very small percentage of the atoms of silicon have actually released an electron with this thermal energy that's available. All right? So that's why we say this is a semiconductor. We don't have an abundance of electrons for current conduction. The ratio of these two is 10 to the 12, 5 times 10 to the 12. It's a huge number. So a very, very, very small fraction of the atoms have released an electron. So a piece of silicon, as I have described it so far, is a relatively poor conductor because we don't have that many electrons available. All right, so we'll say poor conductor. It's still better than diamond because it does conduct, but not as much as we would like it. So what I have described so far is called pure silicon, or more precisely, it's called intrinsic silicon. So a piece of silicon, the way we described it, just a bunch of silicon atoms next to each other, is called pure silicon, also known as intrinsic silicon. Okay, these have the same meaning. If you want to call it pure, that's fine. It's just pure. It's just all silicon atoms in a nice array in the crystal. All right, so now we need to address or familiarize ourselves with one more concept before all of these come together, and that's the concept of holes. So let's talk about that. This is something that you probably have not seen in any courses before because this is so specific to semiconductors. All right, so what are holes? Well, let's change the color of our pen and see what we can do. Okay, so let's again take a piece of silicon the way we have seen it at some finite temperature and observe the following. So let's say we had a piece of silicon here, we had a few silicon atoms and so on, and it just happens that this bond loses one electron. Because of the thermal energy, one electron came out of here and started moving around. So the void that is left behind is called the hole. So there's a hole here because there used to be an electron here, but it's gone. So this bond is missing an electron, and that's what we call a hole. So this is called a hole. All right. So because the electron has negative charge, when it's taken away, this hole has positive charge. All right. So we associate positive charge to holes in the amount that we associate negative charge to electrons. Okay, but something interesting happens. So let's say that I have this piece of silicon, and I take a snapshot. I take a picture of it at time 0. And I see the situation. An electron has just come out of this, and a hole has appeared. Okay? All right. Now, a little later, I take another picture, and this is what I observe. So we just take the same piece of silicon. We have these atoms sitting here. And what I see is that a little later, so let's say t equals t1, maybe a nanosecond later or a millisecond later, it doesn't really matter for us. What I see is that one electron has come out of this bond here and filled this hole here. So now the hole is here. Right? We know that every bond is capable of relinquishing an electron if there's enough thermal energy, and just happens that this bond lost an electron, and this electron fell into this hole, completed this bond, and now we have a hole here. Okay, so we have a hole here. Now let's take another picture a little later and see what happens. So we go to t equals t2 and try the same thing. So again, we have these atoms, silicon here, and so on, and all of these. And it just happens that another electron comes out of this bond and fills this hole. So we have this complete bond here, but then we have a hole here. All right, so in 3 consecutive pictures that we took, we saw that these electrons were coming off of their bonds and filling these holes. Or equivalently, what we can say is that there was one hole, and that hole moved from left to right. It moved from here to here and then to here. And because a hole has positive charge associated with it, we can say that positive charge has traveled from the left side of the semiconductor to the right side as we look at it at different points in time. So we can say a current has been created as we go from here to here. So we say holes are capable of conducting current, just the way electrons are. And that's a very important concept. So when you remember this question that we raised, where do charge carriers come from? Well, we have electrons, but we also have holes. And these two are 2 different entities that can simultaneously conduct current. Electrons can move and conduct current. Holes can move and conduct current. All right. If holes go from left to right, we have positive current going from left to right. If electrons go from left to right, we have negative current going from left to right. So that's something to remember. I also want to emphasize that conduction by holes is not the same as conduction by electrons. So let me raise a question here. Why are holes slower than electrons? Okay, as we will see later, when we give properties to electrons and holes, we say holes are slower, maybe by a factor of 2. Why is that? Well, you can see here that the way this hole moved was actually by electrons being released and trapped. one electron was released from here and trapped here. Then another electron was released from here and trapped here. So it's not like an electron that just shoots through the lattice and conducts current. It's this operation of release and trap of electrons that equivalently allows a hole to move around. And this trap in this release and trap process is slower than just an electron moving on its own without interacting with the other atoms. So we say that hole movement of holes is based on release and trap mechanisms. And that's why it is slower than the movement of electrons. All right, so that's what we have so far. And now we need to look at a few other interesting concepts. Remember that I had this equation for the number of free electrons in a piece of silicon at a given temperature. How many free holes do I have available as well? It's the same number. Because if you take a piece of silicon, for every electron that was released from a bond, we have left behind a hole. So the number of holes and the number of electrons, number of free electrons, are the same in a pure piece of silicon. So we say that the density of holes is the same as density of electrons. I'll just say electrons even though we mean free electrons, and it's equal to Ni for pure silicon. Okay, so that's good to know. Now from now on we will give some symbols to these so that we don't have to write them every time. So the density of holes will be called lowercase p, because it's p-type, is positive charge. The density of electrons will be called n, because it's n-type, and these are equal to Ni for pure silicon. So that's good to remember. We also write p times n is equal to Ni squared. Why? Well, later we will see why we do that, but that's what we need to remember. Okay, all right. So if I give you a piece of silicon at room temperature, you will have 10 to the 10 free electrons per cubic centimeter and 10 to the 10 holes per cubic centimeter. That's it, right? No more, no fewer. All right, but what if you want more? What if this poor conductivity is a problem? How do we modify the density of free electrons and holes in silicon? That is the next question that we need to answer. All right, so that brings us to what we call doping. So let's go and add a page. So we need to answer the following question. How do we modify the density of charge carriers, meaning electrons and holes, in semiconductors, for example, in silicon? Well, right now we're stuck with that 10 to the 10 number because that's what the equation tells us. And we know that the number of free electrons and the number of holes are equal in a piece of pure silicon. Okay, well, to get there, we go back to the periodic table and look at a small section of it to see if there's any other possibility. So let me draw a small piece of the small section of the periodic table. I will look at columns that correspond to 4 free electrons. So we know which those are. For example, we have silicon here, and I think we have germanium underneath, so germanium. We also look at other columns. We have a column with 3 electrons in the last orbital, or with 5 electrons in the last orbital. So we have some elements that fall into this category. For example, boron. So that's boron, which has a symbol of B. Boron has 3 electrons in its outermost shell. Silicon has 4, germanium has 4, boron has 3. And then for 5, we have, for example, phosphorus. Phosphorus, whose symbol is P. So phosphorus has 5 electrons in its outermost shell. All right, so these present interesting opportunities for us to go and play with that piece of silicon. So far I have said it's a pure piece of silicon. But there's no particular reason why it should be pure. What if we go in that crystal of silicon with all those nicely arranged atoms and try to introduce some other atoms, maybe boron atoms or phosphorus atoms? What exactly happens? Something interesting may happen, right? So let's go ahead and do that and see what we get. So here's how it goes. I'm starting with a piece of silicon. So again, we have these silicon atoms that are bonded together and sharing their electrons and so on. And then I go and, in a very controlled manner, add, for example, 1 phosphorus atom here. And then I again have silicon, silicon here, silicon here, silicon here, etc. Okay? So once in a while, I add a phosphorus atom. So what exactly happens in this case? Something interesting happens. The phosphorus atom has 5 electrons in its outermost shell. Now, when it starts sharing these electrons with the neighboring silicon atoms, it shares 4 of them, just like the silicon did before. So this phosphorus atom has 1 electron that is able to share with anyone else, right? There's nobody else who wants that electron. So there's 1 electron that's sort of hanging here because it's an orphan. None of these silicons want it, and the phosphorus has that free electron available. So that electron now can participate in current conduction. That's a relatively free electron that's readily available. So we don't have to break an electron out of this bond for it to conduct current. We already have an electron from this phosphorus atom that can conduct current. So depending on how many phosphorus atoms I introduce into the silicon crystal, I can have a larger and larger number of these free electrons. So I can make this overall device more conductive by having more phosphorus atoms in it. And this process of introducing an atom of phosphorus, or what we call impurity, is called doping. So doping means we take this piece of silicon and then we introduce some non-silicon atoms in here. For example, phosphorus. Okay, so the resulting piece of silicon has a new name. This is called extrinsic silicon, to distinguish it from intrinsic or pure silicon. And that we say silicon is doped, or this is an impurity, or is extrinsic silicon. And then the phosphorus atom itself has a name. This is called a donor, because it donates an electron to this current conduction. So we have introduced donor atoms inside this piece of silicon. And now this overall piece of silicon that has extra electrons for conduction will have a new name. This is what we call an N-type silicon, because it has electrons, more free electrons than pure silicon. and we call it n-type silicon, or we call it extrinsic silicon, and so forth. All right. Okay, so this tells us that we have a situation like this. What's interesting about the situation is that now we can say that if we introduce lots of these phosphorus atoms, a typical number is as follows. So density of phosphorus atoms is about 10 to the 15 to 10 to the 17 per cubic centimeter. So when we dope silicon, typically we choose a number in this range, depending on what we're trying to do. This is considered lightly doped. This is called heavily doped. But no matter, even if we are here, we see that the number of phosphorus atoms that we have introduced is much greater than the number of free electrons or holes that we had in pure silicon. In pure silicon, this was 10 to the 10. Now we have introduced 10 to the 15 phosphorus atoms, meaning 10 to the 15 free electrons coming from the phosphorus atoms. So these electrons coming from phosphorus completely overwhelm the electrons that we had already in pure silicon. In other words, I can say that the number of, or the density of free electrons in this doped piece of silicon, N, is approximately equal to the density of phosphorus atoms. Okay? Because we had some already from the silicon, and now we have a lot more from phosphorus. This is so much bigger, we'll just keep it like that. And this density has a name. We show that by uppercase N and then lowercase d. N is the density of the dopants that we're introducing, and d shows that it's a donor density. So we say that N is approximately equal to ND. All right? And it turns out that also we have N times P is equal to Ni squared. Even this is no longer pure silicon. Of course, we saw that for pure silicon before. But even though N has gone up so much, N used to be 10 to the 10, now it's, for example, 10 to the 15, this product is still equal to Ni squared, the Ni that we had before. Why is that? Well, because P goes down so much, the number of holes available in this piece of silicon has gone down. Why? Because these free electrons that came out of the phosphorus atoms very easily went and filled those holes. So the number of holes is much smaller, and that's why N times P is still equal to Ni squared. All right, so this is what we call an N-type piece of silicon, which is doped to give us more electrons. All right, our time is up. I will see you next time.